Problem 627, Smith Van Ness, 8th edition. Here we have superheated steam at 500 kilopascals and 300 degrees C expands isentropically to 50 kilopascals. What is its final enthalpy? So we're asked to find the final enthalpy of this steam going through this process. And I've got some text here. You can read through it at your leisure. But this is another problem that's going to get you used to working with the steam tables. And this is also kind of a preview of some of the problems that we're going to be doing later on in Chapter 6 and also in Chapters 7, 8, and 9, where we do a lot more process thermodynamics types of calculations. Now we're told that the steam is expanding isentropically. We aren't told anything else about this process. We don't know if this is an open system, say in a turbine or an expander, or if it's a closed system in a piston cylinder device. We just don't know. All we know is that the process is isentropic in that we are asked to find the enthalpy. And so at first this might seem a little disconcerting, but hopefully what you can see is that we are asked to deal with entropy and enthalpy. And you should realize by now that those are state functions. Entropy and enthalpy are state functions, and it doesn't matter what the process is. If all we are concerned about is enthalpy and entropy changes, the process that our fluid is undergoing does not matter at all. All we have to do is calculate changes in enthalpy or entropy, and so that's what we need to do here. So the first thing in doing this is we should focus on this key word of isentropic, and by now you should know isentropic. Another word for, or another phrase for isentropic, is reversible and adiabatic, but we're going to use, generally we'll use isentropic probably a little bit more from now on, especially when we're dealing with steam. So what this means is that this expansion process, whatever it is, there's no entropy change in the steam. That is, the delta S is equal to 0 for the steam. And so that's the key point to this problem. And so what we need to do now is we need to assembling our data, our property data. So just going to write this down. Our T1 and P1, we don't really need a schematic here. Our T1 and P1 is 300 degrees C, 500 kilopascals, and we're already told this is superheated steam. So we're going to go to the superheated steam tables, and we're going to look up. We need to know what the entropy is to start with. All right, we need to look at the entropy and figure out what that is to start with. So we go to our steam tables, back of your book, and at 500 kilopascals, we go all the way over to the right on page 696, and we look up the entropy. So S1 is going to be 7.4614 kilojoules per kilogram Kelvin. So again, be sure you're careful in reading these steam tables. Like I've said earlier, I always have a folded sheet of paper or a ruler or some sort of straight edge to make sure that I'm reading straight across. Also that I'm reading the correct entry. You've got density, internal energy, or specific volume, internal energy, enthalpy, and entropy. For those, make sure that you read the right one. If you do make mistakes, you will get partial credit depending on how grievous those mistakes were, but do all you can to be as accurate as possible, of course. So we've got our initial entropy, and because the process is isentropic, that means our final entropy, our S2, is going to equal to S1. So that's just a very simple little relation there, saying that S2, our entropy of our steam, is going to be 7.461 kilojoules per kilogram. Now, we're asked to find the final enthalpy. So how do we do that? Well, this actually takes advantage of some information that we probably really haven't talked about explicitly, and you've probably forgotten, but the Gibbs phase rule. We are told that the final pressure is 50 kilopascals. And we also know that the final entropy is 7.461 kilojoules per kilogram Kelvin. Because of this, because we now know two properties, everything else for that steam at state 2 is fixed. There's no more degrees of freedom. So what we can do is we can go to our steam tables, we find the entry at 50 kilopascals, and we try to find at what temperature are we going to get an entropy equal to S2. So we go to the steam tables, or if you want to look them up online, you can, but during in-class exams, you aren't going to have that luxury. So get used to using the steam tables. We look at page 692, and that has the entries for 50, some entries for 50 kilopascals. And we look across all those entries and we don't see anything. If we look at that, you know, our first of all, our saturation temperature is 81.35 degrees C. Then our first entry in that table is 7.69, 7.82, its entropy is going up. We go to saturated vapor is 7.59. There's nothing else. There's nothing that's 7.46. All right, so what does that mean? Well, if we look at saturated vapor, it's 7.59. We look at saturated liquid, it's 1.09 kilojoules per kilogram Kelvin. What this means is that we've got a mixture of liquid and vapor in our state 2. So here I've got the saturated vapor, 7.59 kilojoules per kilogram Kelvin. Our saturated liquid is 1.09. Our actual entropy is in between here. And that means that we need to calculate the steam quality or the mole fraction of vapor. And then we can use that to calculate the enthalpy. So this means that our final state is a mixture of saturated liquid and vapor. Again, calculate the quality, and then we'll be able to calculate the final enthalpy. Now, before we leave this, and I'm going to turn my book back to the problem statement or some of the equations in chapter 6, I'm going to go ahead and write down the values of the enthalpy for the saturated liquid and vapor at 50 kilopascals. So I didn't write this down, but these are at 50 kilopascals. So it's 340 kilojoules per kilogram and 2646 kilojoules per kilogram. All right, so now we need to calculate the steam quality, the mass fraction or mole fraction that is vapor. So you've got a couple equations on page 243 that you can use to solve this, and so I'm going to use I like using the form that's equation 696a. And so I'm going to substitute for M, the general thermodynamic property, I'm going to substitute entropy, since that's what we're going after. So what we have is S2 is equal to 1 minus XV times S2 liquid plus XV times S2 at the vapor phase. You can solve that algebraically or ask MathCAD to solve it for you. And we get this equation, solving for the mass fraction, in this case everything's on a mass basis, of the steam, and we get a mass fraction of vapor is 98%. So most of the mass is still vapor, and then all we need to do is simply reapply equation 696 with enthalpy. Only this time we know XV, we know H2 liquid, H2 vapor, and we solve for H2 at the final state, and we get an answer of 2599 kilojoules per kilogram.